Welcome to Math 2318, Section 1.1. In this section, there are a couple of important topics. One is the idea of consistent and inconsistent. A system is consistent if it has at least one solution. It can have one, it can have an infinite number of them. That means the system is consistent. The system is inconsistent if there is no solution. Now, when we look at our system, and here's a nice example here in question 1. Two equations, two unknowns. We write this system as a matrix simply by grabbing off all of the coefficients. The vertical line here is where the equals used to be. The idea is to take this matrix and transform it into a matrix where we can read off the answer, whether that's one solution, an infinite number of solutions, or no solution. So the top line is row 1, we call that R1. Second line is R2, which is row 2. Now, there are certain row operations we can do on this matrix. We can swap two rows, and that will not affect the answers. So swapping rows is a good thing to do. We can multiply any row by any non-zero number. Similarly, you could divide a row by a number. And we can add two rows together to form a new row. So this is how we start off. Where I want to get to is a matrix that looks like ones on the main diagonal, zeros in the other places, and some numbers on the right hand side. In this case, what I have is 0 times x1 plus 1 times x2 is 2, which simply says that the answer for x2 is 2. And then the first one, 1x1 plus 0x2 is minus 8. So I get my solution is minus 8 and 2. So what this means is if we graph this, each of these is a linear equation. There are no powers on the x's. And so if we graph this, we would get two lines. And so the things that can happen with two lines. So let's just make a rough sketch here. So if I have one line here, another line there, they could intersect in one point. I could have the situation of parallel lines, which would mean there would be no solution. And the third possibility is I've got exactly the same line, which means that they're touching at every point. So if we get this situation of ones down the diagonal, zeros everywhere else, we get one solution. All right, so back to my story. I want to use this one to make a 0 under it. Don't worry about the other numbers. Minus 4 times 1 is minus 4, add 4 is 0. So minus 4 times row 1, add row 2, and I'm going to make a new row 2. Let's see, minus 4 times 3 is minus 12. Minus 12 and 7 is a minus 5. Minus 4 times minus 2 is 8. 8 add a minus 18 is a minus 10. So I've got a 1 and a 0. I'd like to get a 1. So I'm going to take row 2 and divide that by 2. And when I do that, I'm going to take row 2 and divide that by minus 5. Minus 5 divided by minus 5 is 1. Minus 10 divided by minus 5 is this 2. So my last goal is to use this 1 to make a 0 above it. So that's going to be minus 3 times row 2 added to row 1. And so when we do that, we get our solution is at the point minus 8, 2. So continuing this in question 2, we have two lines. The question is find a point that is the intersection of the two. So I form the matrix. I simply grab off the coefficients. And now I want to use this 1 that I already have to make a 0. So that's simply minus 1 times row 1, add row 2, make a new row 2. Alright, so that's fairly straightforward. Now I'm going to take row 2, divide that by minus 3, and I get 0, 1, 4. So now you want to use this 1 to make a 0 above it, and that's minus 2 times row 2, add it to row 1. And so what we see is, yes, there is a point of intersection, and that would be at the point here, 2, 4. All right, in question 3, we'd like to solve this particular system. Now, as I grabbed the coefficients, I noticed I had a 1 in this position. So I went ahead and wrote this row first. 1, 4, 6, 6. And then for this one, it became row 2. Alright, so my goal is to, again, to get these 1s down the main diagonal. Alright, so let's see. I'm going to use this 1 to make a 0. I already have one. Use that 1 to make a 0 there. So that's simply minus 2 times this whole row. I'm going to add it to row 3 and make a new row 3. Now by doing that, let's see, I've got a 1 and 2 zeros. I have a 1 here. And so now with that 1, I need to make a 0 above it and a 0 below it. But before I make the 0 above it, I'm noticing something about these two rows. And that is, if I simply add row 2 and row 3, I'm going to make a new row 3. Notice I get 0, 0, 0, and minus 6. So when we get a row of all zeros and something on the right is not 0, that means that we have no solution and the system is inconsistent. Now again, why is this inconsistent? Well, let's see. 0x1 plus 0x2 plus 0x3 is minus 6. So that would say 0 is equal to negative 6, which is not true. So this has no solution. If we were to graph this, we would see that we have 3 planes in R3, and so they don't intersect in a line or a point. Alright, so let's see. Here we have 3 lines. So is there a common point of intersection? So I don't know. Let's see. We grab off all the coefficients and I form the matrix. Now, you should go through the process a couple of times of making 1s and 0s, but after a while, what we really need is an answer. And so you can use Wolfram alpha, and you use the syntax row reduce. So notice I've got the parentheses here, the set brackets on the outside that denotes the matrix. Each of your rows is separated by commas, and inside there are set brackets for each row. And when you type in row reduce, it's going to row reduce the process for you. And so what I see here is x1 is minus 3 and x2 is minus 6. All right, question 5. We have this matrix. So the question is, what value of h would make this a consistent linear system? Meaning that we either get one solution or an infinite number of them, but we want it consistent. So if we do the same process and do row reduce, what I see is how h is involved in the process of figuring out what the answer would be. And so what I'm noticing here is h is in the denominator, and so I don't want that denominator to be 0, so I do not want h to be minus 4. All right. In question 6, we have figure out g, h, and k that will make this consistent. And so again, at least one solution. Now in this case, when I tried row reduction in Wolfram alpha, it did not give me anything meaningful. So you have to know when the tool is helpful and when you need to do it by hand to actually get a feeling for what's going on. So I started off like normal using this 1 to make a 0. So 4 times row 1 plus row 3 to make a new row 3. So I've got a 1, a 0, a 0. Alright, so I'm starting to see how G, H, and K are all intertwined. Now I'm also noticing now something about row 2 and row 3, so I'm going to add those two together to give me a new row 3. So I simply add these together. Now by doing that, what I notice is I've got this row. And if this thing turns out to be not 0, then it would be inconsistent and no solution. If it is 0, so I have a row of all zeros. So row of all zeros. That means that it is consistent, but I do get an infinite number of solutions. So in this case, these three particular planes are intersecting in a line, and so therefore we get an infinite number of points in common.